Any pair of point charges here, indicated as capital Q and lowercase q, stores some sort of electric potential energy. Now I know up until now we've been speaking about electric potential, and we've given that the symbol capital V. Sometimes we calculate differences in electric potential, and we call that a voltage. Here we're talking about electric potential energy. So this pair of charges, capital Q and lowercase q, have some amount of potential energy, and if they're moved closer together, that amount of potential energy increases. If we were to draw in some electric field lines, that would help us relate to this even better, right? As lowercase q is closer and closer, it's sitting in a stronger and stronger electric field. The force that's exerted points in this direction, and so when released from rest, this charge wants to fly off to r equals infinity, and the closer it started, the faster it will be traveling by the time it gets to some position really far away. So this reminds me a little bit of a mass on a spring, right? That also stores potential energy, and if we were to push this block M so that it sits here instead of at the equilibrium position x equals 0, then when released from rest, it wants to accelerate back towards the equilibrium point. Okay, so the elastic potential energy is positive, and in moving the block in this direction, then the force exerted by the spring points this way, but the displacement S is to the left, so the work done by the spring was negative as the elastic potential energy increased. There's a reminder, just in general, change in any potential energy associated with a conservative force is always equal to negative the work done by that conservative force. And of course, work done by any force is the integral of F dot ds. Right, so that allows us to calculate how much electric potential energy there is between a pair of charges, capital Q and lowercase q, if they sit at a distance of r away from one another. Here, let's clean this up. Okay. So here we have it. A charge capital Q and a charge lowercase q, and we'll say from center to center they're separated by some distance r. What's the amount of electric potential energy associated with this pair of charges? Well, in our last video lesson, we said that electric potential at any point B minus the electric potential at some point A is equal to negative the integral of E dot ds as we move from point A to point B. Or if we let VA equal 0, then that means VB is equal to, we can change this to a positive as long as we switch our limits of integration. Okay, so where do we want to let the electric potential energy equals 0. In other words, what do we want to think of as position A? So a common notation, we don't have to do it like this, but a typical one would be, say, let V equal 0 at some point really, really, really far away. Well, anyway, the whole point of calculating values of electric potential is so that we can find values of electric potential energy. Just as electric field is measured in newtons per coulomb and force is measured in newtons, in other words, electric field is to force what electric potential is to electric potential energy. For sure, electric potential energy, like any form of energy, must be measured in joules. Electric potential isn't quite joules, it's joules per coulomb. Yeah, so just as electric field in newtons per coulomb is to force in newtons, electric potential in joules per coulomb is to potential energy in joules. So what's the relationship? The force is just equal to QE, or I suppose it's just as well to say we're defining electric field as being the amount of force per unit charge. It's the number of newtons per coulomb, right? So electric potential energy can be found by multiplying charge times electric potential. Or better yet, I think we're defining electric potential as being equal to potential energy per unit charge. It's not joules, it's joules per coulomb. All right. So this is how we'll do it. We'll find the electric potential at point B due to the charge, capital Q, and then we'll just multiply that times the other charge, right? We'll say this is the electric potential due to capital Q, and then we'll multiply that value times lowercase q to get the potential energy of the pair of charges. And we're letting this point A be at r equals infinity, right? So let's do it. Let's solve for the electric potential at point B. Draw this again. We've got our capital Q here. We know that lines of equipotential go around in concentric circles. Obviously, if we get really far away, we get some infinitely large circle. Okay, so if we're imagining the other charge, lowercase q, is here, then we'll just say this is point B, infinitely far away is point A. The electric potential at point B is equal to the integral of E dot, in general we say E dot ds, but here we can call it E dot dr. What I really mean from B is from R to, and then instead of A, we mean infinity, right? So the electric potential that we're looking for is equal to the integral from R to, oh, sorry. No, this is right. Let's stick with this. The electric field. Now, what's that? Well, the electric field is equal to 1 over 4 pi epsilon naught, or what we sometimes call K, right? Times capital Q over R squared, KQ over R squared dr. So the electric potential is equal to 1 over 4 pi epsilon naught. We can pull the Q out as well, times the integral from R to infinity of R to the negative 2 dr. So V equals 1 over 4 pi epsilon naught times capital Q times negative 1 over R, evaluated from R to infinity. And we can get rid of this negative sign. We can change that to a positive if we flip our limits of integration. I guess I should write that out clearly. So I can say V is equal to 1 over 4 pi epsilon naught times capital Q times 1 over R, evaluated from infinity to R. boy, this is 1 over 4 pi epsilon naught capital Q 1 over r minus 1 over infinity. Of course, 1 over infinity is 0, so we have v is equal to 1 over 4 pi epsilon naught q over r. Now, if you want to call that kq over r just as well. And potential energy is equal to charge times potential. So the potential energy due to a pair of charges, capital Q and lowercase q, separated by a distance of r, is equal to q times 1 over 4 pi epsilon naught, capital Q over r. In other words, the potential energy is 1 over 4 pi epsilon naught, lowercase q, capital Q over r. There we go. Now you might see it written like this. U equals K Q1 Q2 over r. And I say that's the same thing. Okay, well, what if we have 1, 2, 3 charges, Q1, Q2, and Q3. And I want to find how much work it takes to move some other charge, which is Q without any subscript, from a point infinitely far away to this point P. Well, I can say that work done by a conservative force is equal to negative the change in potential energy. Of course, because I said I'm starting from r equals infinity, that implies from a point where the electric potential energy would be equal to 0 to some other point, right? So here's the idea. I could just do this step by step. I could say, okay, I'm going to ignore Q2, I'm going to ignore Q number 3, and I'm just going to figure out what's the amount of electric potential energy associated with having charge Q and Q1 paired up. Now, they're separated by some distance r, so there's an amount of potential energy equal to K Q1Q over this value of R. Maybe I'll call that R1, right? Okay. And then I move this charge here and I say, well, now I'm going to ignore Q1 and Q3, but I'm no longer ignoring Q2. So these are separated by a different value of R. Maybe I'll call this R2, and I'll find the amount of potential energy associated with these two charges. You get the idea. All I'm really applying is the superposition principle yet again. And so the net amount of work is equal to the amount of potential energy associated with Q1 and Q plus the amount of potential energy associated with Q2 and Q, etc. I don't have to stop at 3 charges. Now the beauty of this is that unlike electric field, which is a vector quantity, electric potential is a scalar quantity. You've probably already solved a problem like this one. If I have a charge Q1, Q2, and Q3, fixed in position along the xy axes, and then there's some other point P right here, and we say, what's the electric field at that point? Well, let's just say all of these charges are positive. Then we should represent the electric field as it is, like a vector. So I can represent vectors with arrows. So the electric potential due to charge number 1 is a vector that points up and to the right. The electric field due to charge 2 is a vector that points to the right. The electric potential due to charge 3 is a vector that points up. And so now to find the overall electric field, I'm probably going to have to break E1 into components. So I'm going to leave E3 alone. I'm going to leave E2 alone. But then I'm going to say there's a component of E1 along the x-axis, and there's a component of E1 along the y-axis. And you know where I go from here, and it's going to require a fair amount of mathematics. But if I draw these charges one more time, Q1, Q2, and Q3, but this time I say, what's the electric potential right here? Oh, this is a much easier question. I can't represent the electric potential with arrows because it's not a vector. There's just a numerical amount to it, right? So the net electric potential at this point, by the superposition principle, is just equal to the electric potential associated with charge number 1, the electric potential associated with charge number 2, and the electric potential associated with charge number 3. Okay, so what would that be equal to? Well, that would be K times Q1 over R1 plus K times Q2 over R2 plus K times Q3 over R3. I guess I could factor out the K value and say the net potential is K, and then I'm just left with the summation of, how about Qi over Ri? Why stop with 3 charges? Why not make there a 4th charge? And they don't even have to set on the xy axes. I can have some 5th charge, Q5 over here. As long as I know that every distance between each charge and the point in question, then it's very easy for me to find an overall value of electric potential. And then here's the key to all that. If I want to know how much work is done to take a 6th charge and put it at this point, then I imagine moving some 6th charge that I just call Q from a point infinitely far away to this point P. So the amount of work would be equal to that 6th charge Q times the net electric potential due to all 5 other charges. Sorry, I'm writing too fast. Right. Well, and this is just an arbitrary example. There doesn't have to be 1, 2, 3, or even 4, or even 5. Just we can say that this lowercase q is the additional charge, and everything else is the existing charges. So, like electric field, electric potential is governed by the superposition principle, but unlike electric field, electric potential is an even easier quantity to solve for due to the fact that you don't have to do any vector mathematics. You can just add these values up as scalar quantities.